This module will give you an introduction into electrical and computer engineering. We will concentrate on circuit analysis and explain that using an operational amplifier circuit. But first, let's take care of some definitions. You've probably seen these before, but it's helpful to review. Voltage is a potential across something, such as an electrical component or terminals, such as a wall socket or battery, that type of thing. Each electron contributes an electron volt. Many electrons gathered on one side of a terminal add up to a voltage. This is sometimes considered analogous to the pressure of a fluid, and voltage is measured in volts and is named after Italian Alessandro Volta. It's defined by the National Institute of Standards and Technology using superconducting Josephson junctions held at 4 degrees Kelvin in liquid helium. This is important because voltage is one of those fundamental measurements that we track. Current is the measure of a flow of electrons through a circuit, such as a wire or an electrical component. It's analogous to the flow of fluid in a pipe. Engineers consider the direction of current flow to be out of positive terminals and into the negative or ground terminals of a voltage source or possibly a current source. This is actually in contrast to the physical interpretation of current being electrons that technically flow out of the negative terminals and into the positive terminals. We use this positive to negative flow as convention, and as long as we're consistent about it, everything works out. This is measured in amperes and is named after Andre Marie Ampere. The resistance is a property of a substance that impedes the flow of electrons or currents. A material that has very high resistance is called an insulator. A material that has very low resistance is called a conductor, like a wire. Semiconductors and actual purpose-built resistors fall somewhere in between these. Resistance tends to increase with increasing temperature. For a few materials, resistance completely disappears below a particular temperature. At reasonable temperatures, I'll leave that to your imagination, all materials have at least some resistance, even gold. Niobium, for example, though, is a superconductor below 4 degrees Kelvin. That is minus 269 degrees C. High temperature superconductors lose their resistance below about 70 K or minus 203 Celsius. That's about the temperature of liquid nitrogen. Ohm's law is how we can relate voltage to current and resistance, and is stated as V equals I times R. If a certain current I flows through a resistance R, the voltage developed across the resistor is V is equal to I times R, or the current times the resistance produces a voltage. Conversely, you can determine the current in a circuit by knowing the voltage across the resistor and its resistance. We use Ohm's law in conjunction with Kirchhoff's voltage and current laws. The voltage statement of this is that the sum of the voltages across all components, including your batteries and other voltage sources, in a loop sums to zero. The currents statement of the Kirchhoff's current law is that the sum of all currents into a node sums to zero. So voltage is sums around a loop, and current is focused at a node where we have all the currents into or out of. So here's an example. If we have a 12-volt voltage source or battery on the left, and we have a combination of a 100-ohm resistor in parallel with a series combination of a 200-ohm resistor and a 150-ohm resistor. Now we're interested in determining the currents I1 and I2, along with V1 and V2 voltages. We might also be interested in the total amount of current that has to flow out of the 12-volt battery for this circuit operation. So we can do this step by step. If we look at the 12 volts on the battery here, then we see that as we go around this loop here involving the 100 ohm resistor, that there must be a 12 volt voltage drop across this resistor, where now the positive side of that voltage drop would be on the top of the resistor and the negative would be on the bottom. This way we would have a 12 volt here summing with what's essentially a negative 12 volt there to produce 0 volts around that loop. So now we can conclude that there is 12 volts across this resistor, and we use Ohm's law to say 12 divided by 100 is going to give us the current I1. Alright, so that should be 120 milliamps of current. Now we can move on to this side of the circuit, where we can observe that now 12 plus the V1 and V2, taking account of these plus signs, the order of that. So really it's 12 minus V1 and minus V2 has to sum to 0. So we can add these two together, and therefore we would see that 12 volts is equal to V1 plus V2. Likewise, we can add these two resistors together because we're really interested in I2, and I2 flows through both of those resistors. And there's no other path besides going through both these resistors, so the current must flow equally through both of these resistors. So now we can take V1 plus V2, which is 12 volts, and divide it by the total resistance, which is 200 plus 150, or 350. And that gives us I2. And if I'm remembering correctly, I2 then ends up being about 38 milliamps. Then we can simply take I2 times 200 to give us a value of V1, and I2 times 150 to give us the value of V2. Note that the total current exiting this battery is actually the sum of I1 and I2. This region up here of the circuit is all considered one node. All these wires are ideal wires, and therefore this can all be represented as actually a single point, and therefore the current entering this node must be equal to the current leaving this node. I1 and I2 leave this node, therefore the current coming out of this battery would be a summation of I1 plus I2. Now let's take a look at operational amplifiers, or op-amp for short. Here we have the schematic symbol for an operational amplifier, where we have inputs, where one of the inputs is an inverting input. In other words, if we put a positive voltage here, we'll end up with a negative out here, and vice versa. The other input's a non-inverting input. And then we have the output, and it's an amplifier. It's going to increase the signal. Therefore, we must have some power from somewhere else in order to accomplish that. That's going to come from the power supply. Generally, we would put a positive voltage here and a negative voltage down here. While we don't have time to dive deep into the construction of these very important components, we can study their ideal behavior. We make some assumptions. One, that it has infinite gain. This means that a tiny input causes a huge output. It also has infinite input resistance and zero output resistance. The infinite gain assumption is fairly realistic in that the voltage gain can be on the order of 10 to the 5th. These idealizations have some implications. No current can flow into its input in terminals. This is because it has infinite resistance. Now if we connect, if we look at the circuit and we put the tiniest voltage on the input, because it has infinite gain, we will get a huge output. But if we connect a resistor from that output to the inverting input, then we will force the voltage across its two input terminals to go to zero. This is because we will take that large output signal and run it to the negative input or the inverting input, and this will tend to counteract the amplification that's going on. We call this feedback. I don't have time to explain the virtual ground in a lot more detail, but we can use that as a very common assumption that the voltage in operation between the positive and the negative terminals is zero. So if we create a circuit such as this, using R2 to connect the output to the input, and then R1 to feed the input into the negative terminal, then we, where here the negative terminal is this terminal right here, then let's ground the positive terminal. So now, because we have this virtual ground and we cannot have a voltage difference across these terminals, that makes this point right here actually ground. Okay, so we'll feed a signal in here, and this will be at the ground potential, and then it will get amplified, and a little bit will feed back through R2. Actually, more than a little bit, a lot will feed back through R2, but we will still have an output, as you will see. So the resistor that connects the output to the inverting input feeds back a signal that tends to decrease the output. This feedback results in another implication. There is no voltage across the input terminals. This is called a virtual ground. Since the input resistance is infinite, all of the current entering R1 flows through R2. So now if we can do a little bit of circuit analysis, let I1 be the current in R1 and I2 the current in R2. Let the input voltage be V1 and the output V2. Now we can calculate I1 to be equal to V1 divided by R1, since the junction of R1 and R2 is at ground. Recall that the positive terminal is at ground and the negative terminal is at the same voltage as the positive terminal, so we have this virtual ground. From Kirchhoff's current laws, we can observe that I2 is equal to I1. This is, again, because no current flows into the input terminal of the amplifier. So there's nowhere else for that current to go but right through resistor 2. Therefore, we can calculate the voltage at the output, and that's equal to the current I2 times the feedback resistor R2. Well, we know that I1 equals I2, so let's substitute in I1 for I2. Now, we previously calculated V1 divided by R1 is equal to I1, so let's substitute that in here, where we have V1 here and R1, and we'll notice that the output voltage V2 is equal to the input voltage times R2 over R1. The R2 over R1 is what we call gain. How much does the output voltage gain from the input voltage, right? So we see that the gain of this simple circuit is R2 divided by R1. Notice that it is not a function of the op-amp gain itself, but only a function of the resistor ratio. The signal still travels through the amplifier, and the minus input, or the inverting input, inverts the output, changing positive values to negative and vice versa. So in summary, Ohm's law and Kirchhoff's laws are important tools to analyze circuits. If we make some assumptions about the ideal behavior of an op-amp, we can see that they make great amplifiers where the gain is simply a function of a resistor ratio. We can choose R2 and R1 within reason. So the ideal assumptions still have to apply, but we can choose that ratio to create an amplifier of almost any gain. Thank you.